All right. Okay. So thank you for the invitation. I'm Sharan, and this is joint work with my students, Michael and Martin, and our collaborator, Anand. Okay, so let's start. So policy gradient methods are widely used in practice. Theoretically, we kind of understand that the objective is non-concave, and under certain smoothness assumptions, you can prove convergence to a stationary point. Recently, there have been these papers which show that under in certain settings, like for a tabular parameterization, vanilla PG just running like reinforce or natural policy gradient can actually converge globally to the optimal policy. Okay? But if you look at these methods, there are like a couple of problems. One of them is that they require oracle knowledge about the environment. So some of these methods require knowledge of the optimal action or the reward gap in a multi-arm bandit problem to set algorithm parameters, and you can't run them. Others require conservative choices of algorithm parameters, which if you run them result in poor empirical performance. So what we wanted to do in this project is try to design practical methods that retain theoretical guarantees and you can actually run them on problems. So that's a broad aim. In this talk, I'll just focus on stochastic, softmax, unregularized policy gradient methods in the tabular setting, including bandits, and with a focus on developing practical algorithms. Okay, so we want to solve, say, multi-arm bandit problems by just running policy gradient. Okay, so the structure is, first I'll just get started with, so we are in the discounted setting, finite states and actions. D pi is the state occupancy measure. And as always, we are maximizing the discounted return. So given a set of policies capital pi, so maybe I can use a mouse, the objective is to maximize this j pi. For this talk, like I said, we are only going to focus on the softmax tabular parameterization, which means that there are s times a parameters theta. The set of policies, capital pi, consists of all these softmax policies where pi of a given s is proportional to exponential of theta sa. Okay, so this is the class of problems we want to focus on, and just see, at least for this class, can we do something like practical or like tending towards practical. Okay, and to make life easy, I'm just going to abstract out the objective as f of theta, and the hope is that we will recover or we will get what assumptions we need about f so that we can extend them to like other problems. So we don't have to like go through this whole process again. I'm just going to see what assumptions or what properties of f do I need to prove global convergence. Okay. So across papers in the past 3-4 years, you can abstract out these properties of this function f for, say, finite MDPs. So we know f is twice differentiable, but it can be non-concave in theta for this softmax case. Then the other kind of condition that is satisfied is f is uniform smooth. So the Hessian can be bounded by L times the identity. And for example, if you consider bandit problems, L is like phi over 2. Okay, so typically, L is like some number which is known that does depend only on like the discount factor. The other kind of property that you can abstract out is that the Hessian, like the function is non-uniform smooth, meaning that the Hessian can be bounded in terms of L1 times the norm of the gradient times some identity matrix. Okay, so this is kind of nice because it tells you that as you get closer to a stationary point, the landscape becomes flatter and flatter, and this potentially allows you to use larger step size. Okay, so again, for a bandit problem, L1 is equal to 3. There is some complicated expression for MDPs as well. Okay. The last type of condition that will be helpful for us is that this function f needs to satisfy some non-uniform Loasovich condition. Okay. So this is like a gradient domination condition. So the gradient is dominating the suboptimality. Compared to the standard PL condition, you should notice that there is no square on the gradient norm. Okay, so it's a Loasovich condition, but it's not like the Polyak Loasovich condition that we know of. The other thing to notice is that it is called non-uniform because there is a c of theta over here. So it's not a constant. It actually depends on the parameter theta at which you are. Okay, so again, for bandit problems, c of theta is proportional to the probability of pulling the optimal arm. Okay, so c of theta is not known. You should ensure it does not vanish to 0. And then with this condition, you can actually prove global convergence. Okay, so that's the kind of properties we would need in order to prove global convergence. So for MDPs, I'm just going to assume the sufficient exploration assumption. So this is similar to the May et al. Paper or Agarwal's paper in the beginning, which says that the starting state distribution has like full support, and hence this mismatch ratio, the C infinity, is bounded. Okay, so this will just allow us to focus on the optimization aspects without worrying about exploration, at least for now. Okay, so given these properties, what do we know about softmax policy gradient, where I can assume access to all the rewards, all the transition probabilities? Okay, so the algorithm is simple. Just do gradient ascent on this function f of theta. Eta t is the step size. For finite MDPs, this is exactly the policy gradient, which consists of like d pi, pi of a given s, and the advantage. Okay, so this is for the softmax parameterization. Okay. So L is like the smoothness. So bandit problem, say, is pi theta transpose r. That's the softmax objective for bandit problems. So it's like the probability of pulling an action multiplied by the reward. So that function, as the function of theta, is phi over 2 smooth. So I just wanted to say it's smooth. So okay, so let's first assume that the gradient can be calculated exactly. If not, there are some estimation. You can account for estimation errors, but just to keep life simple. And in this case, let's see what is known. Okay, so what is known for softmax PG? So if you run the algorithm with a step size of 1 over L, L, remember, is the smoothness. For 1 over epsilon iterations, it will indeed ensure that f star minus f theta t is less than equal to epsilon. Okay, so there is like a small thing here, or like an important thing here. There is a potentially large constant hidden in this O. So for bandits, it's not a problem. For MDPs, this constant can scale exponentially in the number of states, and that actually is the price you have to pay for not exploring. Okay? So, but people still use softmax policy gradient, and we are going to see what we can show in terms of like the rate of convergence. Okay? So in practice, using a step size that depends on this global smoothness L is often too conservative and results in poor empirical performance. So this is kind of known. On the other hand, you might say, okay, look, there is the rate of convergence is only order 1 over epsilon. If you run policy iteration, for example, that converges linearly and requires log 1 over epsilon iterations. So you can actually, so there is this paper which can achieve log 1 over epsilon iteration convergence by just normalizing by the gradient norm. So you step in the direction and you normalize by the gradient norm. As the gradient norm decreases, the effective step size increases, and you can achieve global convergence in log 1 over epsilon iterations. Okay? This requires setting this eta to be like 1 over L1, where L1 is like this non-uniform smoothness constant. And this depends on like the distribution mismatch ratio, and which we don't know. Okay, so if you want to compete against policy iteration, you can't run this algorithm as of now. Okay, so this is the kind of things we will want to do in this talk, is try to see if we can get rid of these dependencies on L and L1 so that we can actually implement these. Okay, and as an aside, natural policy gradient with exact line search does converge at a linear rate. Okay, so let's handle the first problem. So L is conservative. Using a step size of 1 over L is conservative. If you talk to an optimization person, they will tell you to do a line search. So let's do a line search. So this is like the standard backtracking Armia line search, which says that the function value after doing the update needs to be larger than the function value before. It should be sufficiently larger, where how large depends on the gradient norm. Okay? And h is some hyperparameter which we are going to set to be like half. Okay? So this automatically guarantees that eta t is greater than something which scales as 1 over L. So you're using step sizes of 1 over L, and h you can just set it to be half. Okay? So set eta max to be very large, and this gives you large step sizes. The question is, if you're being so aggressive in the algorithm, does it still converge to the optimal policy? And the answer is yes. So this is a theorem from our paper, which says that if you use backtracking Armio line search with t equal to order 1 over epsilon iterations, you can still get the same guarantee that f star minus f theta t is less than epsilon. Okay? And the proof is like pretty standard. Use the Loasevich property with the standard Armio line search for smooth functions. And the tricky part is to ensure that the non-uniform Loasevich constant c of theta does not vanish. So you actually converge globally to the optimal policy. Okay? And in fact, if you run this on bandit problems, c of theta is going to start increasing at some iteration t naught. And if you start with a good initialization, it's going to start increasing right from the first iteration. Okay? So all is good. And if you run this, it will indeed converge to the optimal action. So again, the problem is, okay, this only gives us order 1 over epsilon convergence. Can we design a line search that can exploit the non-uniform smoothness and actually converge at a log 1 over epsilon rate? Okay. So the idea is that if my f, so in our case, this f is L1 non-uniform smooth, this alternate function g of theta, which is the log of the suboptimality, which is f star minus f theta, is order L1 uniform smooth. Okay? So if I make this g of theta converge at a 1 over t rate, this guy is going to converge exponentially fast. Okay? So that's the basic idea. And this is similar to the logistic loss. So the log of the logistic loss is like 1 smooth. And you use this, if you have seen these papers, which are like these edge of stability papers, they use this log loss to argue that you can use like much larger step sizes. Okay, so now the idea is, okay, let's just do backtracking line search on g of theta. So you can design a line search procedure which says that the log of the suboptimality needs to decrease sufficiently, needs to decrease by a sufficient amount. And again, it is proportional to f theta. But notice here now there is an f star minus f theta t. Okay? So the above procedure, if you run it, will guarantee that the step size which is returned by this line search is greater than the min of n eta max, and something that is now scaling as 1 over f star minus f theta t. So as this guy is going to 0, the step sizes are increasing, and this is again getting you the benefit of, or is like kind of simulating this normalized gradient descent, but without knowing any unknown constant. Well, f star still needs to be known, but that is easier to estimate. Okay, so again, you can prove the same thing. Backtracking line search using the Armio condition, log 1 over epsilon iterations, does ensure this theorem holds. Okay, so like I said, similar. So this is similar to the Polyak step size, which assumes knowledge of f star. This arguably is much easier to estimate than the mismatch ratio. In our experiments, we just set it to like 1 over 1 minus gamma if the rewards are between 0 and 1. Okay? And if you do run this, you will find, given a starting state distribution with full support, this SPG plus the line search can attain linear convergence, and it matches the performance of like policy iteration. Okay? So you can run it, it converges fast, matches the rate of, even in practice, policy iteration. So we have like designed at least like one kind of practical algorithm, but this is for the setting when we can compute the policy gradient exactly. Okay? So the next part of the talk is when we cannot compute the policy gradient exactly and can obtain only like unbiased estimates. Yep. Yeah. That's right. That's right. So if you overestimate it, it's too aggressive. If you underestimate it, it can get stuck. In practice, overestimating is okay. That's what the polyac step size, like the papers in which use the polyac step size also do. So they underestimate the loss, like they set it to like 0. But yes, this is the problem. We tried a little to get rid of this F star, but at the moment we are not able to. Yeah, that's a good point. Yeah. Right. So if you choose this eta max to be very large, it does backtrack. So it won't just like converge in one shot or like it does backtrack. So you do see it backtracking. But if you set 1 over like eta max to be like 10 to the minus 10 to the 5, for example, yeah, it just hits it in one shot. So in that case, it is like very similar to policy iteration. Yeah, we tried messing with like the state distribution to like kind of see if it does not converge in like 2-3 iterations. Yes, and experimentally. I guess this was like an experimental statement. So yeah.
Since experimentally it matters, do you think something is missing from the theory? You're not testing the worst case examples, or?
Yeah, I think we are not testing the worst case example.
But do you think there's a set of examples on which you might be able to prove a polycircuit SAA?
So I think if you start with a very bad initialization, this will get stuck. Yeah. So you can make, like you can put the probability of pulling the optimal action to be like epsilon, and then make this thing stuck. Yeah. Yeah, I should ask Michael to do that. Yeah.
So effectively, if you had if you first run something that you have reasonable initialization, something uniformish or whatever, and then run this, so warm-up procedure, maybe you might be able to get a poly everything log 1 over epsilon, right?
Yeah, so one idea is that you run it with entropy regularization for certain iterations, get to a decent thing in like the middle of the simplex, and then run this.
Does entropy regularization give you guarantees in terms of
the log 1 over epsilon?
Well, I guess no, in terms of the poly SAA.
Yeah, there is no pi theta a star in there. So for the banded problem, there is like, yeah. So the constants are better. But there are still some constants that I don't remember off the top of my head. Yeah. Okay. So let's move to the stochastic setting, which is arguably more important. So in this setting, we cannot compute the policy gradient exactly and need to do so via interactions. We will require the policy gradients, like the stochastic policy gradients, to be unbiased and have bounded variance. Okay, so these are standard assumptions. Wherever you see a tilde on top of F, that's the stochastic policy gradient. So an example throughout is multi-arm bandits, for which F theta is pi transpose R. In this, the overall algorithm is that you sample an action according to this policy, calculate the importance sampled reward estimate. RT is the reward you get when you sampled the particular arm at this particular iteration. This ensures unbiasedness, and then just calculate the gradient in the usual way. Okay, so this is like on policy. So you're using the policy that you are updating to sample the arms. So in this case, this gradient is unbiased and has bounded variance. The bounded variance can be bounded by like 2 for rewards in 0 and 1, and you can do the same thing for MDPs. Okay, so in this case, the stochastic softmax PG is, again, you update your parameters in this direction. And let's see what is known. Okay, so here the story gets a little tricky. So for stochastic SPG, the first thing I should say is that in the stochastic on policy setting, both natural policy gradient and this normalized policy gradient thing are too aggressive. So they will commit to a suboptimal action very quickly, and in fact, there is like some non-zero probability of failure. Okay, so these are like these papers which say that either you are fast in converging in the exact setting and you fail, or you are slow in like order 1 over epsilon, and then you will do the right thing by exploring enough, by pulling all the arms enough. Okay, so stochastic SPG, like the things which we know are that if you set the step size proportional to the norm of the gradient, norm of the full gradient, then with these many iterations, you will get epsilon convergence. Of course, the full gradient cannot be computed in the stochastic setting. Another paper by Yuan et al. Says that you should set eta that depends on mu. Mu in turn depends on c of theta. C of theta in turn depends on pi theta a star, so you can't implement this. Okay, so that's not good. Yeah. Oh, so C in the bandit case is proportional to the probability of pulling the optimal action. Oh, so it's the constant for the Loasevich condition. Okay, so again, with t over 1 over epsilon cube iterations, this can get you this bound. But again, mu is not known, and you cannot implement this algorithm. So we are kind of stuck at this point. So the question is, can we design a practical stochastic SPG method, say at least for bandits, that gives us global convergence and does not require setting parameters according to like these unknown problem-dependent constants? Okay? So the observation is this thing that we want is actually equivalent to constructing a step size schedule for SGD when minimizing a smooth non-convex function satisfying some particular gradient domination condition, but you cannot use the knowledge of mu. Okay, so mu is pi a star, you cannot use the knowledge of mu, and now the observation is that this is the equivalent problem. Okay, so how do we solve this? In a separate series of papers that I was working on, this is exactly what we end up doing. So this says you fix the number of iterations you want to run it for. Choose a step size which is some constant eta 0, say 1 over L, multiplied by alpha t, where the alpha t's decrease exponentially fast. So this is alpha to the t. But alpha depends on the number of iterations you want to run this for. Okay, so, and this was first proposed by this very nice paper by Lee and Francesco. And this shows with this step size, it lies somewhere between constant and 1 over t. Okay, so if you plot it for like a finite t, where the t is fixed, these step sizes are going to lie somewhere in the middle. So they are not as aggressive as 1 over t, but they are still decreasing. And the other important thing is that the capital T needs to be fixed beforehand. Okay. So with these step sizes, when in fact you use it with SGD for functions satisfying the PL condition, you will get convergence, and none of these step sizes require the knowledge of mu. Okay. So it seems that the stochastic policy gradient problem that we have can be solved by using these step sizes up to a thing that compared to this stronger PL condition, our optimization objective is weaker, satisfies only a weaker gradient domination condition. And of course, there is this non-uniformity in terms of like the C of theta that we don't know. Okay, so for a given epsilon in 0 and 1, so I guess the thing you should take away from this slide is that if you run stochastic SPG with a step size which is exponentially decreasing, setting t equal to 1 over epsilon plus sigma square over epsilon cube iterations suffices to converge to like an epsilon neighborhood. The rate is sort of noise adaptive. So if you have rewards which are not varying as much and sigma is small, then this algorithm will converge faster. If sigma is 0, it retains the 1 over epsilon rate. When sigma is non-zero, in the worst case, it actually matches the 1 over epsilon cube complexity in like these other SGD papers. Okay, so then in this way, it is like because you know capital T beforehand, you can trade off the bias and the variance in a smarter way and get like this noise adaptive rate. Okay, so ensuring that mu is greater than 0 requires ensuring that this probability is greater than 0. This is true for any finite t, and actually even asymptotically this is true. So you will converge to the optimal arm if you just run this algorithm with these particular step sizes. Okay, so but the problem is the rate depends on mu, which as we discussed can be large because of like the initialization or the trajectory. So there is still like some unknown or like problem dependent, potentially large constant hiding there. Okay. So any questions about this? Yep. Oh, sorry. Yeah. No, I don't think so. It's like saying can normalized stochastic gradient work in like can normalized gradient work in the stochastic setting. So unless you do couple it with like some variance reduction thing, I don't think so. Oh, so to get the log 1 over epsilon thing, basically it's like normalized SGD because the step sizes were so aggressive. And in the stochastic setting, if the noise itself is not going to 0, it is not going to work. But on the next slide, we will see that the noise itself is going to go to 0. So that's my like final slice. Yes, Pancha. So it's like you set t to make this term order epsilon. Yeah, yeah. Okay, so the rate is still slow in terms of like t compared to like these other papers. And the question is, can we get a 1 over epsilon rate in the first place, and then maybe we can make it faster. Okay, so in this case, the stochastic gradients do satisfy the strong growth condition, because as the optimization progresses, you are trying to converge to a deterministic policy. So as a function of theta, the variance is actually going to 0. And this paper by May et al. Actually characterizes how quickly this is happening. So they established this strong growth condition, which says that as you're getting closer and closer to a stationary point, like the variance is also going to 0. Okay? And this is going to be great, because now we don't need to decrease the step size. The entire reason we needed to decrease the step size was to counteract the variance. The variance itself is going to 0, so now we can converge with a constant step size. And this is what this paper shows. So it shows that if you set eta that depends on this strong growth condition constant, you will converge to an epsilon neighborhood in 1 over epsilon iterations, and everything is going to be fine. But as you can guess by now, the problem is this rho depends on the reward gap, which we don't know, and we can't set the step size. Okay, so same question. Now, can we take the algorithm that we have designed, the one which uses these exponential step sizes, and show that at least can it achieve a faster 1 over epsilon rate? Okay, just by, because we know, and the idea is, we know that the algorithm is adapting to the variance is going down, so maybe by just doing a more careful analysis, we can get convergence at a 1 over epsilon rate. Okay? And this theorem does say that, so it says if you have knowledge of rho, then you will get the 1 over epsilon rate. If you set eta 0 to something large, initially you won't converge at this fast rate, but overall you can converge at a 1 over epsilon cube rate. So in this sense, using like these exponential step sizes makes stochastic SPG robust to this choice of rho. So if you can nail down the rho exactly, you will converge fast. So you don't lose anything compared to a constant step size. If you do not know rho, instead of diverging, it is just going to slow down. Okay, so this is like some additional robustness that these exponential step sizes buy you. So your rate can basically interpolate between something which is like 1 over epsilon and 1 over epsilon cube, depending on how you set eta 0. Okay, last one. Okay, so for the bandit problem, what are these constants? Actually, it turns out to be very easy. You just set eta 0, like the starting step size, to be like less than 1 over 18, use importance weighted reward estimates, and you converge. The result does not require any problem-dependent constants, no explicit exploration, and in practice, it kind of works well, but not amazingly. So the blue line and the green line are like these oracle methods that use unknown things, and the red line and the orange line are like two variants of our method. The red line is the one which uses like a doubling trick. So you set t and then keep doubling it instead of setting it once beforehand. So that allows the method to be more aggressive, and this kind of works. Okay. So step sizes, practical variants. We have similar results with entropy regularization, where also the existing results needed knowledge of like reward gaps in order to like trade off, in order to converge to the optimal policy. Still quite conservative. So at this point, I was kind of irritated with this smoothness and strong growth condition and trying to find step sizes that satisfy all these things. So we were asking, can you use constant step sizes which are much larger than those that are guaranteed by smoothness and this strong growth condition? And this was 3-4 months ago when this adjustability paper also came out for logistic regression. And we were like, maybe in our case also this could be a reasonable thing. And the answer actually is yes. So with this paper, with Jin Cheng, Bo, Alek, Anand, Dale, and Chaba, we show that stochastic SPG with any step size, it could be potentially large, does converge to the optimal R. We don't have a rate. We don't know what happens non-asymptotically, but we know as t tends to infinity, you will do the right thing for any large step size eta. Okay, so okay, and that's my last slide. Getting stuck in plateaus is a side effect of using these softmax policies. So one thing we should try to do is change the policy class, and then of course it's like generalizing to have function of